chapter 6, we talked about how microbes grow. In chapter 7, we're going to talk about the control of microbial growth. When we talk about control, we need to define some terminology. These are words that you've probably heard and have even used: disinfecting, sterilizing, degerming. However, they each have their own unique meaning, and therefore people may not be aware of the absolute term that these should be applied to. So when we say things like cleaning, disinfecting, sanitizing, what's really the difference? When we speak of these things, cleaning really is just physically removing dirt and grime. Yeah, as you do that, you may get rid of some of the germs that are on the surface, but it's not necessarily going to be something that's truly antimicrobial. Sanitizing reduces germs on surface by that cleaning, but for the most part, this is just to a safe standard. So when we talk about sanitizing, this is very applicable in like the food industry. You want to wipe everything down, making sure that in places like nursery schools and daycares, that things get wiped. So these are going to reduce the germs. If you're truly disinfecting, this means that you're killing a high percentage of germs. And therefore, when we talk about that deep cleaning, that is a little bit more important. When we think about some of these surfaces that might be cleaned, these might be things like our bathroom surfaces and toilets, diaper areas. Those are going to be things that we expect to have contamination, and therefore usually using products that are meant to actually kill. The problem with a lot of things is that they can look clean, but there may still be germs there. We don't like to think about it, but if you look at a child's high chair, sometimes there's 1,500 times more fecal bacteria than the child's potty. Why? Well, we think about that bathroom area and we disinfect it, but we probably only sanitize and wipe down that high chair. The average home office desk probably has more than 20,000 germs per square inch. Again, we tend to, at best, clean, maybe sometimes sanitize, but we're usually not going through and disinfecting the things around our house. It's also estimated that the telephone earpiece and mouthpiece may carry up to 1,400 bacteria. That's just things that we deposit, whether it be our normal flora or transient organisms. However, it's a great reminder, if you haven't done it in a while, clean your phone. So what are the differences between these types of products that get used? A cleaner obviously aids in helping to remove dirt. So although it may remove some germs with it, it definitely isn't something that's going to kill. Sanitizers reduce the number of bacteria. So you're lowering the microbial count to what is usually a safe level, but it's definitely going to be that there's organisms still there that can be problematic. When you truly talk about a disinfectant, this is meant to kill fungi, bacteria, and viruses. When this happens, not everything may be killed, especially things like bacterial endospores, where those are more resistant. And depending on the types of environmental surfaces, disinfectants may not be equally effective on all surfaces. Virucides are specifically for viruses. Again, we usually think about trying to inactivate viruses on the multitude of inanimate objects that we find in our environment. Sterilants, we don't usually do a lot of sterilization in our homes. That's usually more clinical. So a sterilant is going to eliminate all fungi, bacteria, viruses, and endospores that are important. So that's why when we talk about a sterilizing agent, this is going to be something that is going to remove all living things plus the bacterial endospores. When we talk about the control of microbial growth, sepsis technically refers to microbial contamination. The problem is that we think of the clinical form of sepsis, which usually means bacteria growing in the blood, But if you think about it, the term does make sense from the standpoint that blood should be sterile, so having microbial growth is sepsis. It's just that most people think of the form of sepsis in the blood than thinking about it from the standpoint of microbial control. So therefore, asepsis, when you put that A in front of it, means the absence of significant contamination. That's why both in clinical situations and in the lab, we have to practice good aseptic techniques. So in a clinical suite or surgical suite, you do a lot of implementation to make sure you're preventing microbial contamination of wounds by making sure that you're using clean everything and washing and using gloves. In the lab, we kind of do the same thing. So we try to prevent the contamination of cultures. If we want to identify an organism, we have to have a pure culture. And therefore, if we start to contaminate with other organisms, we're not going to be able to identify. It would be mixed, and therefore our results wouldn't make sense. So we do things like flaming the loops, disinfecting the bench top, flaming the mouth of the tube so that bacteria and other things in the environment don't end up contaminating our nice pure cultures. So some of the terminology that you are familiar with, just to make sure that you understand their definition. Sterilization, as we said, is the removal of all microbial life. Commercial sterilization is, in the food industry, killing Clostridium botulinum endospores, which means that those could potentially cause botulism. Disinfection, killing of pathogens, and when we think about that, that is on objects and surfaces. If you're removing those pathogens from living tissue, then we refer to that as using an antiseptic. So antisepsis is meant for biological things. We also do kind of a subcategory of that, what's referred to as degerming. Degerming is the removal of microbes from a limited area, and the classic one is when you think about when you give an injection, you take an alcohol prep and you rub down the area. We're not trying to get rid of everything that's there, but you're trying to remove a number of microbes, especially things potentially transient that could be a pathogen, so that the area is at least degermed or cleaner than what it was before. In the food industry, we often rely on sanitization. Again, our eating utensils, we do things to make sure that we lower the microbial count. Even if you go to the nicest restaurant, those knives and forks and things that you're using haven't necessarily been sterilized. So we expect that there's not a whole lot of bacteria there, that they have been sanitized, but they haven't been sterilized. When we talk about our agents for disinfecting and for doing things to remove bacteria, we can talk about the difference between biocides, which actually kill, and things that are bacteriostatic. So if we have something that's simply inhibiting, that may be good enough as long as you don't have increasing numbers, but technically different antimicrobial agents, some are going to be germicidal and some are only going to be bacteriostatic. We'll also talk about the way organisms die. So the rate of microbial death is also important to think about when we're doing microbial control agents. Bacteria pretty much die the same way that they grew. So if you look at the graph here, when we talked about microbial growth, we said it was a J-shaped curve. So the blue dashed line represents when you're simply just counting the bacteria. So you're looking at the arithmetic number and plotting that on the scale against time. Same way as when we talked about that J-shaped curve, you have a period of time where it looks like things are not there, but when we look at that 4-minute time point, there may still be significant bacteria there. We can see this better when we start to do things on a log scale. The same way as what we talked about for microbial growth, bacterial populations die at a constant logarithmic rate. So having that nice straight line, the pink line on this graph, gives us a way to be able to use its predictive value and a much easier way to actually look at the numbers. So on the arithmetic scale, when we looked at that 4-minute time point, it looks like everything's flatline and nothing's there. However, if you actually look at where the 4-minute time point intersects with the log number, you see using the pink line that this could actually be 10 to the 2. And so there's literally 100 cells that could be there. Some infectious diseases, the organism may cause infection with less than 10 bacteria. Therefore, not counting those 100 bacteria could be problematic. When we use a log scale, we usually talk about that a 1 log decrease is killing 90% of the population. 90% sounds great when you're thinking about exams and grades and things. And in theory, 90% is also great when you're talking about killing bacteria. However, you need to be thinking about what that 90% means. So when you talk about reducing something, 1 log, decreasing 90%, if you start with 10 to the 5th organism, so that's 1 with the 5 zeros there, that is actually 100,000 bacteria. A 1 log decrease takes you down to 10,000, but that's still a lot of bacteria that you need to be concerned about. That's why when we look at the example of microbial exponential death rate, we need to know how many we're starting with. So when we start at time 0 and we have 1 million bacteria, when we do that 1 log decrease, we have killed 900,000, but there's still 100,000 left. So that's why it's important to think about how many bacteria are there before we start. Each time we do a log decrease, we keep getting rid of 90%. However, depending on what you started with, that could still be problematic. So that's why when we talk about the effectiveness of antimicrobial treatments, we really need to think about the number of microbes. The solid pink line represents a population that has a high microbial load, and therefore a 1 log decrease from 10 to the 5th to 10 to the 4th still leaves significant number of bacteria present. However, if we look at the dashed line that has a low population load, if you do a 1 log decrease, well, going from 100 to 10 is much more significant than that where you're still talking about things with a high population where you could still be talking about tens of thousands of bacteria. As well, the environment that the bacteria is found in. If bacteria or other microorganisms are associated with organic matter, they're going to be more difficult to disinfect. So when things are in fecal material or mucus, that means that that is protecting those microbes, and therefore you're either going to have to leave things on longer or have more potent chemical means to disinfect. So the same thing can be said about those biofilms. We said biofilms, they form that hydrogel, and that becomes this kind of protective layer so that antibiotics, and in this case disinfectants, it's very hard for them to get in past that biofilm to be able to actually kill the bacteria inside. As well, we know temperature, pH, affects our ability to handle or kill our microbes. So in general, we think about heat for killing. pH extremes are often detrimental to microbes as well. And as well, things like times of exposure. If you're working with a culture up in the lab, even a test tube that had bacteria growing overnight can have 10 to the 9th cells per mil in that tube. So if you spill that on the benchtop or on a book or something, you're just not going to be able to take a paper towel and simply wipe it up. You need to expose it to a disinfectant for a while to make sure that you're actually disinfecting the area. As well, we're going to see the microbial characteristics matter. Some things are just easier to disinfect than others. So gram-positives are actually easier to disinfect than are gram-negatives, and therefore understanding the microbes that might be present in that environment is important. So we're going to take a look at the action of antimicrobial agents, so how they control the bacteria, and basically, where do we hit them? When we talk about the action of microbial control agents, some things are going to work on the membrane, simply affect its permeability, puncturing holes so that cells become leaky. But we can also damage their proteins. If a cell needs to carry out enzymatic activity or they have structural proteins, any damage to those proteins are going to affect its viability. And as well, we can damage the nucleic acid. So damage the DNA, RNA if organisms aren't able to replicate their DNA, or they can't make RNA to be able to carry out translation into proteins. Obviously, all of this is going to kill the organisms. Physical methods of microbial control are often very effective and commonly used. So we'll talk about the difference between using heat versus low temperature, and we'll also look at some other things like osmotic pressure and radiation. When we talk about heat, heat is a great physical method of controlling microbes. It is going to denature their proteins and effectively kill them, usually in a fairly short time. So from the standpoint of thinking about this, whether it be in the food industry or other means of trying to evaluate a disinfectant, we need to kind of set parameters. Thermal death point is defined as the lowest temperature at which all cells in a culture are killed within 10 minutes. We want something that's going to be able to work very quickly and at a reasonable temperature. Thermal death time is the time to kill all cells in a culture. So whatever time it takes, that is what it is. We oftentimes do a decimal reduction time. This is the number of minutes to kill 90% of a population at a given temperature. So when we looked at that log decrease before, that is a good way to actually measure. You can hold the temperature constant at something that would be reasonable, and then look at how long it would take to kill one log or 90% of that population. In order to sterilize, we usually have to provide something that's going to penetrate better, and that provides steam heat. Here we see a picture of an autoclave. An autoclave is going to be used for sterilization, and it generates steam heat at very high temperatures. Specifically in an autoclave, we have steam under what is 15 psi, pounds of pressure, and they get up to 121 degrees Celsius. This is enough to achieve complete sterilization, meaning it's going to kill all endospores from things like Clostridium botulinum, Clostridium tetani, and Bacillus anthracis. So it's going to kill all living things. The problem with an autoclave, though, is that things that are heat liable, you can't put in there. Therefore, if you have some plastic that's not going to tolerate that type of heat, you can't use that to be able to sterilize it. Unfortunately, we have some plastic artwork up in the lab of times where people didn't realize that the plastic they were using could not be autoclaved. However, in general, this moist heat is going to be able to penetrate not only the living bacterial cells, but even the endospores to kill everything. We always have to check the autoclaves, so there's always a temperature check, and you have to periodically also do a spore check to make sure that it is achieving complete sterilization. So we need to do this all the time to make sure that we are sterilizing our media and other things up in the lab. For a limited amount, so a simple flask, this can be done in as little as 15 minutes, so it's quick and effective for sterilization. Pasteurization, on the other hand, is not going to B, complete sterilization. Pasteurization is meant to reduce spoilage organisms and pathogens found in various dairy products. So we can talk about equivalent treatments. There is the original pasteurization temperatures that were around 63 degrees Celsius or 145 degrees Fahrenheit that were done for around 30 minutes. We now have newer, improved procedures. High temperature short time can be done at 72 degrees Celsius or 161 degrees Fahrenheit for about 15 seconds, and ultra high temperatures, 140 degrees Celsius and 284 degrees Fahrenheit for literally a second. Even at these types of equivalents, thermoduric organisms that survive heat are still going to survive. That is why your milk, any other products that are pasteurized, they are still going to have microbes present. You're increasing the shelf life, but you're not getting rid of all microbes. If you did that, milk that had been completely sterilized would just not taste like milk anymore. However, there is some issues with the pasteurization techniques that are used. When you do low temperature pasteurization, kind of that normal pasteurization at about 150 degrees, we see that this pretty much allows some of the proteins to still survive. So the majority of enzymes and nutrients are going to be kept intact. When you get up to these high temperature pasteurizations and these ultra pasteurizations, these very high heats actually start to get rid of the enzymes and proteins, and people may have problems digesting these types of products. So oftentimes people may not realize how that milk or other dairy has been pasteurized and may have problems with it just because of the different procedures that have been used. So those ultra pasteurizations really can be problematic for the fact that they damage proteins and vitamins that we want to have in our milk, so it is a trade-off. However, in general, pasteurization is good. We wanted to get rid of the bacteria that might be present, especially those that are pathogenic. It's also going to maintain the flavor of the milk over time. And most importantly, this is going to increase the shelf life. People always think about that organic is better. And I don't want to imply that it's not, but part of this needs to be discussed in the reality of our lives. Most of us do not live on the farm anymore, so raw milk may taste great, but it's meant that you're getting it fresh from the cow and you're going to then drink it right away. When you start to talk about things having to go from farm to a processing to a store, then to our table, all of this means that there's a longer period of time where organisms are going to be able to grow. So in New Jersey, there had been a move in the early 90s that people were these raw milk advocates. They were presenting testimony that said, raw milk is better for you, and very few people actually become sick. However, the Center for Disease Control countered with studies that had been done in the late 1980s and said, no, what are you talking about? They documented that there were at least 130 some outbreaks due to the consumption of raw milk and raw milk products. This led to over thousands of illnesses, hundreds of hospitalizations, and things such as death, stillbirths, and miscarriages. So when you have these microbes being able to grow unchecked in these unpasteurized products, that's problematic. Some of the germs that have been linked to raw milk, things like Campylobacter, E. coli, Salmonella, are ones that you may recognize. Listeria is the one that is mostly causing the problem for the unborn fetus, so those stillbirths and miscarriages. That's why we need to educate people about the danger of unpasteurized products. When we talk about things like Campylobacter, E. coli, Listeria, Salmonellas, and Yersinia, these are things that make people sick and are the common organisms in raw milk and raw dairy products in the United States. Outside of the United States, unpasteurized dairy products may also contain Brucella, which can cause a undulating fever, mycobacteria. These tend to be more severe types of flu-like illnesses. They may have recurring fever and night sweats and cough. And so therefore, outside of the United States, the organisms that are found in unpasteurized products can be more problematic. In the United States, most of these organisms cause some intestinal distress, but they can be very problematic for people with weakened immune systems, or elderly, or very young, or people with HIV, AIDS. So we need to be careful about the distribution of these products. And as I said, bacteria, especially the Listeria found in raw milk and raw dairy, is especially dangerous for pregnant women and their unborn babies. Other physical methods: dry heat sterilization kills by oxidation. In the lab, we flame our loop before we use it to streak plates. Incineration is, again, burning things. That's going to kill a number of organisms. Hot air sterilization. But as we talked about with the autoclave, steam heat, that moist heat, is always going to be better, or at least quicker, and at lower temperature compared to its hot air equivalent. So if we look at two equivalents, if we want to sterilize with hot air, we have to get up to 170 degrees Celsius for 2 hours. That means the products that we are trying to sterilize may be damaged by temperatures that high. Autoclaving, you can achieve the same equivalent treatment for sterilization at a lower temperature of 121 degrees Celsius for only 15 minutes. So therefore, moist heat usually is better, quicker to be able to kill not only the bacteria, but the endospores. We talked previously in our growth chapter about things like filtration. Well, filtration is also a physical method for controlling microbial growth. In the previous chapter, we used filtration to be able to trap the bacteria on a filter to be able to count them. In this case, we're not interested in counting them. We just want to remove the microbes, but the same principle applies. In general, low temperatures inhibit microbial growth, but things are not necessarily killed. You know, refrigeration is going to just slow things down. It's not necessarily going to be something that is actually bactericidal. And as well, in the previous chapter, we talked about things like deep freezing and lyophilization, that deep freezing with vacuum. Those are going to allow bacteria to be preserved so that if you add broth or nutrients to them later, they would grow, and so therefore it's inhibiting their growth but not killing them. We also discussed things like desiccation and osmotic pressure. So high pressure in general denatures proteins, but desiccation is going to prevent metabolism. When we put things into hypertonic environments, high salt, high sugar, we saw that plasmolysis occurs. And so that means that the organism is not going to be metabolically active, so it's a great way to control microbes, especially in food. The kind of forgotten method of physical control is radiation. Radiation damages DNA. Some radiation is very penetrating. Ionizing radiation, like X-rays, gamma rays, electronic beams, they are going to be very penetrating, as you know, and obviously very damaging. When we talk about controlled microbial growth, oftentimes what's more realistic is using non-ionizing radiation, such as UV. The backside or the downside to that is that it's not very penetrating. You know that if you put just even a cloth or something, that can prevent UV from going through. So UV radiation is a great surface sterilizing agent, and that's why we use it, for example, in biological hoods. After we're done working, we turn on the UV lights to sterilize the surfaces as we have left things there from working with our microbes. So we see that the non-ionizing UV radiation in the diagram below, that the bactericidal range is from 200 nanometers up to about 300 nanometers. We also start to see some of the issues of UV and sunlight and tanning. But in general, when we think about UV, it's going to potentially be damaging whether we're talking about microbes and their DNA or eukaryotes such as ourselves. UV is still going to be damaging. When we talk about microwaves are much longer, but the problem is that they do kill, but they're not especially antimicrobial. When you think about microbes, when you think about microwaves, they're meant to be heating things, and that's why we use it for cooking so much. However, you're doing it in such a short period of time, it's just not especially antimicrobial. We have been trying to get more use of UV radiation because in theory, it's good for the environment to not have to use a lot of chemicals or other things. And this is an example of trying to convince the people in the meat industry to utilize things like UV radiation. We see in the spectrum of light that, again, the portion of UV light that is the most bactericidal is what is referred to as UVC. The peak of killing is going to be at a wavelength of 260 nanometers, and that is what's effectively used. So you see ultraviolet reduces levels of pathogenic bacteria in meat, things like E. coli, Listeria, Salmonella. So it sounds great, like this should be used. However, if you say that you have used radiation on our food products, people in the meat industry, the general public, they get very nervous about that. They don't understand that the radiation is not staying with that product, and so they may be hesitant for using these types of procedures. That's why you see things like the graph where using the effective properties and saying that when you use that UVC radiation, it increases your profits. That's because your meat's going to last longer. It's not going to spoil as quickly because of the organisms that are present there from the slaughterhouse, and trying to then say that this is not only good for the product itself, it's also good for your profits. It's important to remember, though, that when you talk about these UVC systems, they're going to have to be used in areas where people are not present. So when you have the carcasses hanging on meat racks, or you're storing cuts in some type of shelving units and things, these types of UV lights can be very effective in trying to remove the microbes from the surface. If you remove the microbes from the surface, even if you turn that piece of meat into ground beef, for example, it can also help because what was now to the outside, when you grind it up, gets to the inside. So use of UVC radiation can be very effective in definitely trying to decrease the microbial load in our meat products, both in and on. So now we're going to talk about chemical methods of control. When we do some of the testing up in the lab, we typically take a agar plate and make a lawn of bacteria, then soak the disc in some disinfectant, put it on the plate, incubate the plate overnight to allow the bacteria to grow, and then we look for zones of inhibition where the antibacterial agent has killed the bacteria around the disc. So this is what's referred to as the disc diffusion method, and this is common practice in the lab. However, when we're talking about chemical methods of microbial control, as we said before, we still have to be thinking about those principles of effective disinfection. The concentration of the disinfectant is important. In general, greater the concentration, the more effective, but usually we often get things more concentrated and dilute it down to an effective range. As we said, organic matter, if present, is harder to disinfect. This becomes especially problematic in clinical situations. pH, that can affect the action of various chemicals. So if you have something that is going to change the pH of the area that you're disinfecting, that chemical just may not be as effective. And as we said, time. The longer the exposure, the more microbes that die. One of the early of the chemical disinfectants was phenol. So phenol is especially effective against gram-positive bacteria that we might have on our hands. However, it's quite irritating in its own or its original form. But because it was one of the oldest of the chemical disinfectants, we often see that other methods are compared to phenol. You may see things have a phenol coefficient rating. If it's more effective than phenol, then it's given a phenol coefficient of greater than 1. If it's less effective, then a phenol coefficient of less than 1. We can also do what's referred to as a use dilution method. In this, we're usually taking something like metal rings that have been dipped in a test bacteria, and we dry the bacteria on the rings. These are then placed in a disinfectant, and we can do different dilutions of the disinfectant and do this for 10 minutes at a set temperature of 20 degrees Celsius. The rings are then transferred to culture media, and we then see if it grows or not. If you watch the little video there, you see those that are getting cloudy or turbid were not very effective in killing the organism. We also do things in a multi-well plate as seen on the left-hand side. It's a little bit different than that traditional use dilution test, but however, we may want to be able to see a wider range of dilutions and just do things in smaller volume. So this is commonly employed as well when we're trying to determine what dilution is effective. The tried and true way that we talked about for the disk diffusion, though, is often still the way to go. With the disinfectant, you simply dip it into a solution of that disinfectant and then place it on a agar plate where you have put a lot of bacteria. Again, when you place the disk on, the bacteria has not grown up yet, so you then incubate that overnight and then look for the zone of inhibition after the bacteria has grown. The larger the zone, the more effective that disinfectant is. So we see here that you typically would want to test against a typical gram-positive and a typical gram-negative. So that's why we see the disk diffusion being done on Staph aureus, our typical gram-positive, and E. coli here, our typical gram-negative. When we look at the zones of inhibition, we see something like chlorine seems to be effective against both the Staph aureus and the E. coli. However, the hexachlorophene works against the gram-positive, the Staph aureus, but really doesn't do anything against the E. coli. O-phenylphenol is the active ingredient in Lysol, seems to do fairly well against the gram-positive and gram-negative. But when we look at the quat, that is definitely better against the gram-positive. So we want to make sure that we're looking at this from both what are the expected microbes to be there when we pick our chemical disinfectant. So some things are going to be better against gram-positives, some are better against gram-negatives. The plate to the right-hand side is Pseudomonas aeruginosa. Pseudomonas aeruginosa is particularly problematic in a number of clinical situations because it's very resistant to antibiotics, but it's also very resistant to disinfectants. So it's a gram-negative rod, but it's not the typical one like an E. coli. That's why we often give special consideration to Pseudomonas aeruginosa when we're testing and saying something is an effective disinfectant. So in the example seen here, the only thing that's even minimally working against the Pseudomonas aeruginosa is the chlorine. It's also important to remember the information or the idea of dilutions. Here we're looking at a typical disinfectant, the Zephyrin, and they did a disk diffusion test of the Zephyrin against Mycobacterium abscessus. This mycobacterium is what's referred to as a rapidly growing mycobacterium that's commonly found out in the environment. So it often is a major source of infection for various wounds. Here we see an example of an infection following a steroid injection. The point being that if you have the undiluted form of the Zephyrin, it was good at decontaminating or killing that microbe, but even diluting that 1 to 10 means that it's no longer effective at all against the bacterium. So that's why it's important to make sure that you're utilizing the appropriate dilution. So now we're going to look at some of these specific antimicrobial chemical agents. You need to really remember this chart. This is going to look at the microbial characteristics and how easy or difficult it is to disinfect these various forms of microorganisms. The most resistant at the top here is the prions. Prions are proteinaceous infectious agents. Think of things like mad cow disease is the thing that comes to mind for most people. We'll talk about them when we talk about the viruses, but suffice it to say, since they're not living, they're very difficult to disinfect, and that was the problem when we started to worry about our beef becoming contaminated with these prions. Next, in the most difficult to disinfect are the endospores of bacteria. Things that produce those endospores are the Clostridium and the Bacillus. Remember, Clostridium is the anaerobic gram-positive rod. Bacillus is the aerobic gram-positive rod. Going down the list, mycobacteria, so things like Mycobacterium tuberculosis, but we also see problems with the rapidly growing mycobacteria, things like the Mycobacterium abscessus that we saw in the previous example. We'll talk next week about our protozoa. The vegetative form of protozoa is the feeding living form. However, if they are in an adverse environment, they will form a cyst, so it's basically a resting stage. The cyst form of protozoa are more difficult to disinfect than the living feeding form. Going down our list, gram-negative bacteria like E. coli and Enterobacter and Salmonella are kind of in that moderate range for being able to disinfect. Then fungi and including their spores. Viruses without envelopes are a little bit more difficult to disinfect than viruses with envelopes. So an envelope is kind of like a membrane around the virus. And if we look at the viruses with lipid envelopes, COVID-19 fortunately has an envelope. That's the good news, is that even though this is a highly infectious agent, the fact that we can easily kill it is important. However, right above the viruses with those lipid envelopes, the gram-positive bacteria, things like our Streptococcus and our Staphylococcus, fortunately, those are also pretty easy to disinfect. So that's why when we talk about what organism is there, we see gram-negatives like E. coli are in general going to be more difficult to disinfect than gram-positives like Staph aureus. That is why it's important to test against both the gram-positives and the gram-negatives. So what are some of the chemical disinfectants? As we said before, we sometimes use a phenol coefficient to compare others to, for the fact that this is one of the oldest. Phenol is also known as carbolic acid. You see the picture of the phenol there. It's a 6-member benzene ring with a hydroxyl group. True phenol is quite irritating. If you get it on your hands, it actually burns and will do a lot of tissue damage. And it has this very organic type of odor to it. It denatures proteins, which is why when you get it on your skin, it does the damage. But we still use it in some forms in a very, very, very dilute amount. So, for example, if you have a throat spray, that tingle might be from the fact that it has a very small amount of something like this carbolic acid. Most of the time, though, our disinfectants are going to have derivatives of the original phenol. So things like phenolics. These are going to be things like O-phenylphenol, which is the active ingredient in Lysol. This took that original phenol and added on another 6-membered ring. These are very good at disinfecting. They injure membranes and actually are even effective against the mycobacterium, which is important. And they're good with organics and very stable. That's why Lysol kind of got its claim to fame around places like the bathroom. If you lived in a time before you had disposable diapers and you had a baby around, then disinfecting the nursery because of potential fecal contamination with those organics. All those things were important, and so that's why Lysol became this kind of household cleaner. When we talk about the bisphenols, it took, again, that original phenol ring and then had a linker in between. If we look at the hexachlorophene, a typical bisphenol, there's the carbon in between, but for the triclosan, there's the oxygen in between. But you see the pattern of what those two rings, the bisphenols, look like. These are oftentimes common cleaners, and they disrupt plasma membranes. In a clinical situation, you may have heard of something referred to as Physohex. This is commonly used in the nurseries and hospital to control gram-positive organisms, things that you're likely to have on your hands. Remember, when babies are born, they do not have any microbial flora, so as they're passing through the birthing canal, that's their first introduction to what they will pick up as their flora. And that's why it's important that we are careful about what they get exposed to in those initial days in the nursery. There is a disclaimer here of excessive use can cause neurological damage, which sounds odd that you might use this in the nursery. However, that would literally mean you would have to be literally bathing babies in it almost constantly on a daily basis. So again, in practicality, it's not problematic, but you do always have to have the disclaimer. Triclosan has gotten a little bit out of control in its use or overuse. It is incorporated into so many products. So we see in the corner picture some of the products that have triclosan that you may use on a daily basis. It is also being incorporated into kitchen cutting boards and handles of knives and plastic kitchenware. Plastic kitchenware is disposable. Like, why do we need to be putting these types of reagents in there? There had been some concern about these triclosans being able to have byproducts during processing that are similar to endocrine disruptors. That could be a potential safety concern. However, the FDA, the Food and Drug Administration, they've tested and they do not see a problem with these triclosans, but for a while there was a lot of concern about these kind of products. The biggest problem is really with the overuse, and now we're getting a number of resistant strains. The more you put things out there, the more likely things are going to become resistant. The bisphenols, triclosan in particular, again, this is going to inhibit the formation of lipids, so it's hitting the organism at the membrane, and they're especially effective against the gram-positives, things that would be likely on the skin, but it does work on most gram-negatives and fungi. Again, our problematic organism, our Pseudomonas aeruginosa, it's not killed by these types of bisphenols. Biguanides, again, are going to disrupt plasma membranes. They're these long chains, almost looks like a spread out paperclip or something. You may be familiar with it in what is referred to as chlorhexidine. This is a broad spectrum scrubbing agent, so it's used for surgical skin preparation and surgical hand scrubs. You know, before surgery and some other clinical procedures, there's a very specific hand washing procedure that clinicians follow. And use of these biguanides, things like the chlorhexidine, is very important. It's not just the run-of-the-mill soap that's being used. We also have a new waterless pre-surgical scrub, Avogard. This has been approved for hospital use, but most hospitals are not using it. But this would be important in areas where maybe you don't have access to running water to be able to do the pre-surgical scrub. So when you've had a natural disaster or on a battlefield in war zones and things. And so these types of products could be lifesavers. They have a strong affinity for skin or mucous membranes, so that's why it's good to be using it as that surgical skin preparation. The problem, mycobacteria are relatively resistant, so you still have to worry about those especially rapidly growing mycobacteria that can be present in the environment. And endospores and protozoa cysts are relatively resistant as well. You can even find some of these in some of the mouthwash products as well, as seen here. But when I think about the biguanides, I definitely think more about the surgical scrubs than anything else. Halogens are another very common type of disinfectant that's used. The ones that are used typically are iodine and chlorine. These are oxidizing agents that combine with tyrosines, basically to impair protein synthesis. It used to be that everybody had a tincture of iodine in their medicine chest. So this was a little glass vial and had a little glass wand in it that you could coat that on a cut or a scratch. This is basically an aqueous alcohol solution that contains the iodine. The iodine, if you've ever used anything with it, you know that it's very irritating, but it's also really messy. It stains that brownish, orangish color. The newer varieties are what are referred to as iodophores, iodine plus organic molecules. They're not as irritating and they still stain, but not as much. Betadine is a common one that you're familiar with. It's a povidone iodine, and this is used in a lot of clinical situations, but can also be used for things like water treatment. I myself am a Clorox person rather than Lysol. Part of it is just the smell. When people associate clean with not only things looking clean, we also have that smell of clean. For me, it's bleach. So I like Clorox products just because, yep, they are a good disinfectant, but I just appreciate that smell as well. So chlorine, true bleach, is hypochlorous acid. The Clorox is the sodium hypochlorite form, so that's kind of their proprietary brand. We can also have liquid forms of compressed gas of chlorine, and that's what we use to disinfect drinking water, swimming pools, sewage. So chlorine gets used a lot. You may have also seen chlorine dioxide. Chlorine dioxide is a gaseous form, and that means it's more penetrating. If it's more penetrating, not only can it kill live bacteria, but it can also kill endospores. You may have also seen things like this potable aqua, which is basically chlorine dioxide that is going to allow for water purification when you are out hiking or various other things when you don't have access to municipal water supplies. So this is going to, or if the municipal water supply gets contaminated, these types of tablets can help to disinfect so that you have good, clean drinking water. The regular water that comes out of the tap often contains what are referred to as chloramines. This is chlorine plus ammonia. It allows for the stable release of the chlorine over long periods of time so that you get a longer range of time for disinfecting. This can be used for glassware and utensils, but we also use it for our water treatment in general, and it helps to control the taste and odor problems from the reaction of chlorine with the nitrogen products that would otherwise occur. The other issue, because of these chloramines that are found in our tap water, it has definitely been a problem for those fish, the goldfish that you won at the festival. It means that the water is toxic to aquarium fish, and if you put them in there without realizing and put them into water right out of the tap, unfortunately they will end up belly up. We also see that the chloramines can be found in a tablet form as well, what's referred to as Chlorofloc. These are used as tablets by the military, again, to provide potable drinking water when you don't have access to the tap. Alcohols are a go-to in clinical situations for disinfecting. We see ethanol and isopropanol are the typical forms. Ethanol is a higher grade, so usually more expensive. Isopropanol is the cheaper kind of rubbing variety. These are going to denature proteins and dissolve lipids, so it's very effective as a biocide. In the graph here, we see the effective concentration of ethanol on Streptococcus pyogenes, which is the causative agent of strep throat. Interestingly, when you have something that is 100% proof, it is not bactericidal. You need a little bit of water for it to be effective. Therefore, the effective range is between 60% up to 95%. The 95% is a higher grade and therefore more expensive. So that's why we typically see rubbing alcohol at 70%. It's of note that it's not effective against endospores and non-enveloped viruses. Remember, we said before, COVID-19 has an envelope, so that's why people have been talking about the use of alcohol and those types of disinfectant wipes and hand sanitizers and trying to combat the COVID-19 pandemic. So that brings us to an obvious question. Should you DIY your hand sanitizer? I'm sure we've all seen the empty shelves of trying to find hand sanitizer right now. And so people have started to say, make your own. So the key to getting this right is the ratio. The CDC has said that the hand sanitizer needs to contain at least 60% alcohol as the final product. And that has quality control for store-bought brands to make sure that it contains at least that amount of alcohol. So the problem is when you make it at home, what happens if you get the amount wrong? They recommend that you should measure the concentration of alcohol in the final product using an alcoholometer. Most of us aren't going to do that. So therefore, the problem of their concern for people that are making their own. Most recipes use a mix of 91% or 90% isopropyl alcohol, which is the rubbing alcohol, and mixing that with aloe vera to provide this as a moisturizer since alcohol is very drying. So the hope is that if you have this higher percentage, that is going to then be at an appropriate amount by the time you do the making of the recipes. Typically, the ratio is 2/3 rubbing alcohol to 1/3 cup of the aloe vera. And if you start with a higher percentage, hopefully you get it right. However, if you don't use enough alcohol, the final product won't be as effective. And so therefore, the CDC and the World Health Organization have been saying if you're making your own and you're not sure you're getting it right, it's probably just better to wash your hands. We also have things like heavy metals. The heavy metals work by what's referred to as oligodynamic action, which means it just takes a very small amount to be able to kill. They denature protein, and so we see things like silver and copper and zinc being some of the heavy metals that we use. Things like lead pictured there would not be used, and we're also finding things like mercury, which used to be used but no longer is recommended because of the toxicity problem. You used to find mercuric chloride, and that was often common in people's medicine cabinets back in the day, but we now know better. One of the things that is noted in the lower right-hand picture is mercury was used in making felt more pliable so that hatters could actually mold it to make the hats. So that's why we got the term mad as a hatter, because people that were hatters were constantly being exposed to mercury and ended up with some severe neurological problems. So no more mercury, but things like silver and copper and zinc are still very effective. People of my generation, when we were born, we had 1% silver nitrate put in our eyes to prevent the potential infections from things like Neisseria gonorrhea. We now use antibiotics instead of the silver nitrate, but we see silver is still being used in a variety of different forms. Burns patients are especially susceptible to infection. They have had the skin layer removed as that protection. For a number of years, I worked at one of the Shriners Burns Institute in the microbial lab, and obviously we saw the worst of the pediatric burns. And unfortunately, when patients survive the initial burn, it doesn't mean that they are out of the woods. They oftentimes succumb to the multitude of infections that can occur. That's why having these types of products that can be incorporated into dressings, because it's such a small amount, these have been quite effective. So we've seen taking silver and a sulfa drug and incorporating them into these dressings. That means that you're putting this on these large areas that may have been burned and no longer have that protective skin layer, and helping to prevent infection. We also see products like Surfacine. These contain silver and a iodide. This is a product that can actually coat surfaces. So it's selectively delivering the silver, which is a broad spectrum antimicrobial, by putting it on these applied materials. So it's applied as a thin, clear antimicrobial coating, and it gives us long-term antimicrobial efficiency or efficacy. And so therefore, this is a nice surface kind of antimicrobial that has been used incorporating the silver. You may have come across things like copper sulfate is a common algicide. Zinc is in galvanized metal and in paints, and we see copper and zinc in things like shingles, anything to try to prevent these from becoming contaminated with microbes, whether it be bacteria or fungi. You can often see if something actually contains a heavy metal by doing a variation on that disc diffusion that we talked about previously. So if you take a coin or a charm and you want to see if that has real copper or silver in it, you can make a lawn of bacteria, put the coin on there, and then let the bacteria grow up. If you get a zone of inhibition, that means that you actually had the heavy metal present in that material and are demonstrating oligodynamic action. Again, it doesn't diffuse far from the coin, so you're not going to have large zones just because it doesn't diffuse very well, but you can clearly see the zone of inhibition. Other things that you've come across, quartz. Quartz are quaternary ammonia compounds. Things like the Zephyrin we talked about in a previous slide, and Cepacol is a mouthwash that's kind of one of the older varieties. I grew up using Cepacol, and it kind of has a very strong taste to it, but you're probably more familiar with seeing quartz maybe at the hairdresser or the barber shop. That blue solution that combs and scissors are often soaking in, those are quartz. They're strongly effective against gram-positives, which would be what gets deposited from hands onto those types of scissors and combs and things. Unfortunately, our pseudomonads are resistant to the quartz as well as spores in our mycobacterium, but we tend to use it for a number of things. We also, in the United States, use this cetylpyridinium chloride for a poultry wash. This is to, again, try to remove some of those gram-positives. It is allowed in the United States. However, European countries do not allow this type of poultry washing, so we have to make sure that products that we may send abroad, how they have actually been handled, because a number of countries will not accept poultry that has been disinfected in this way. So when we talk about the quartz, these are going to be bactericidal, so that differentiates these cationic detergents from things that are typical soaps and other acidic anionic detergents. Various soaps and acid ionic detergents are sanitizing, meaning that they decrease the numbers, so they do skin degerming, but the quartz are actually bactericidal. Here is what is found in the Zephyrin, and if we look at a comparison, we see soap and water really doesn't do much to decrease the percentage of bacteria that survive. It's good at dislodging and removing things, but it's not exactly going to kill very well. The aqueous Zephyrin, a dilution of 1 to 1,000. The hash line there, it's better than soap and water, but certainly not as good as a tincture of the Zephyrin that has some alcohol in it, and not as good as that 1% iodine in 70% ethanol, what is referred to as a tincture of iodine. Other disinfectants that you know, aldehydes are really for tissue preservation. When you think formaldehyde, that is typically what we used when we had the animals that were preserved for dissection. Things like glutaraldehyde, what is referred to as Sidex. These are very potent disinfectants, but they are very irritating. Some of the newer ones are referred to as OPAs, the orthophthalealdehydes. They, again, have the same action of inactivating proteins by cross-linking functional groups, but again, these are fairly harsh types of disinfectants. Gaseous sterilants are important because they're highly penetrating. They denature proteins, so things like ethylene oxide are excellent sterilizing agents. They are going to completely kill. You often found in the underbellies of hospitals that there were these big gas chambers to disinfect medical instruments and equipment and things like that. However, these are potential carcinogens. So we have now learned that we need to be much more careful in the limited use of these types of sterilizing agents. They still need to be used because some things cannot be used in high heat. They would simply break down, melt, and they're not as penetrating. But we need to be careful and make sure that those that are handling these types of gaseous sterilants are not going to be exposed because of the potential for developing cancer. As well, peroxygens are good oxidizing agents, and that means that they're good at getting rid of bacteria. So O3 is ozone. It is used for disinfecting water. In the food processing and medical equipment sterilization, we often use what is referred to as peracetic acid. It's one of the most effective liquid sporicides. So that way, if you have these types of equipment, that obviously you need to make sure that you're getting rid of the spores from things like Clostridium botulinum in the case of food processing, but even for medical equipment, you don't want spores of things like Clostridium tetani around. So being able to use this peracetic acid on food processing and medical equipment is very important. You may be more familiar with a peroxygen, which is benzoyl peroxide. It's very effective against the anaerobic bacteria that's usually found in our pores and causes acne, and that's why it's incorporated into many over-the-counter acne medications, but it can be effectively used on wounds as well. Everyone used to have hydrogen peroxide in their medicine chest, but we have found that hydrogen peroxide is actually now labeled as a poor antiseptic, but a good disinfectant. It is very good at killing microbes. However, we've now realized that it can inhibit wound healing, so that's why we don't want to use it as an antiseptic anymore. There's also what are referred to as plasma gas sterilization. These types of newer technologies are important for aseptic packaging. These new technologies are very important when you have things that are not going to be easily sterilized by our traditional methods, whether it be heat or these other chemicals. This plasma sterilization is an excited gas of low temperature hydrogen peroxide. It creates free radicals that are going to destroy microbes. This is very important when you have various things that need to be sterilized, such as medical equipment, and then you have things that are one-time use and packaged. So we're always looking for new ways to be able to do this type of sterilization. Drexel actually has a plasma institute that specifically studies this type of sterilization. Supercritical fluids have also become important. It's taking a combination of chemical and physical. So you take things like carbon dioxide and compress it so that it has the properties of both a liquid and a gas. And this can be highly penetrating for use with medical implants. And plants are notorious for becoming infected, especially with biofilms. So trying to develop these new technologies are very important. We also see issues for things that are from donors. There actually is really not a regulated way to go about not truly trying to achieve antisepsis, but to make sure that bones and tendons and ligaments that are harvested aren't contaminated with harmful pathogens, whether it be bacterial or viral. And so this is not really regulated. So you've seen examples where these types of donated tissues have caused problems. So looking at these type of supercritical fluids that can possibly get rid of these potentially dangerous pathogens on bones and tendons and ligaments that are being donated, because you have to maintain these as living tissue. Therefore, most of the other types of chemical disinfectants or antiseptics are not going to be useful. In the Part B slideshow, we'll talk more about some of the chemicals that are used for food preservatives. Organic acids such as sorbic acid, benzoic acid, calcium propionate, these all inhibit metabolism and help control molds and bacteria in foods and cosmetics. For meats, one of the things we add are nitrites and nitrates. These prevent endospores from germinating, so the endospores from things like Clostridium botulinum, the causative agent of botulism. The interesting side effect, though, is that incorporation of these nitrites and nitrates helps the meat to retain that red color. So the meat seen there, both of those are the same age of meat, but the one on the right has been treated with the nitrites and nitrates, and it retains that nice red color. So trying to get people to have nitrate-free or nitrate-free ground beef is problematic, not only for the fact that, one, you probably do want it in there to prevent the germination of the endospores, but people just like that red color. We've come to expect that of our meat products. We also incorporate a lot of antibiotics in many of our dairies. Cheese, for example, we make it by fermentation using microbes, but then you don't want the spoilage organisms to start again degrading that product. So things like niacin and the netamycin, these are put in our dairy cheeses to prevent that spoilage. So it's very important that you remember the microbial characteristics, that rank order that we talked about, from things like endospores being the most difficult to disinfect and down to our enveloped viruses like COVID-19. But the top priority of the endospores and the mycobacteria means we always pay special attention to those chemical agents that are able to disinfect those two categories. So we often compare things for their ability to disinfect endospores and mycobacteria. It's always a trade-off. You have something like the bisphenols where there's no activity, but the phenolics, you get poor activity for endospores, but good activity against the mycobacteria. Things like chlorine, fair for both, but if you look at the iodine-containing things, poor for endospores, but good for mycobacteria. So you need to know what you're expecting as you try to decide what is going to be the best chemical agent of choice. We also see issues with our green products. To quote from Kermit the Frog, it's not easy being green. The effectiveness of green products depends on what you're trying to do. These green products are cleaning agents. They are not antimicrobial. They do not kill microorganisms, so they're not disinfectants. They have plant-based things in them, so that allow them to be good at cleaning. It is a true statement that if you are cleaning areas better, you probably are removing some of the germs that may be present, but it's important that people realize that they are not disinfectants. They are not actually killing any of the microbes, and that might be something that you want to think about. So right now, When you're dealing with COVID-19, using these green products may not be the best idea because you're solely relying on being able to clean and wipe away the virus. You want something that's actually going to kill it, so you want to rely on the chemical disinfectants, things like our Clorox and our Lysol. Those are going to be the best disinfectants at this time. So you want to make sure that you go through and understand the various categories, their modes of action, and their unique properties, as I've tried to highlight in the slides. And also just check your understanding. So the check your understanding questions are often interesting because it just makes you think about things. How is it possible that a solution containing 1 million bacteria would take longer to sterilize than one containing 500,000 bacteria? Well, it depends on the bacteria. If it's a mycobacterium, then it's going to be harder to disinfect and would take longer, and you would have to make sure you had the right type of disinfectant than maybe your run-of-the-mill E. coli. When you think about other things like a can of pork versus a can of soup that also has some pork pieces, well, it would take longer for that more solid pork. You would, again, have to think about the ability of that temperature to be able to penetrate to the core. And so all these things have to be considered when you're thinking about control. What's the product where you're trying to control the microbes? As well, which is more likely to be used in a medical clinical laboratory, a use dilution, or a disc diffusion? I kind of think that depends. You can see here that for some of the things, this happens to be an antibiotic ones, but some of these are already incorporated into strips that they just lay on there. We've talked more about disinfectants than antibiotics. We'll do that in the next. But even for something for the dilution, well, you probably are going to want to do something quick and easy, but dilution does matter. So I kind of think this is one where it depends on the situation, but probably in a medical clinical laboratory, if you don't have the ability to automate things, you may be better served by just doing a disc diffusion. And just a reminder, alcohol is an effective reagent against viruses, but not all. So it doesn't kill as easily those that do not have an envelope. But fortunately, our COVID-19 does have an envelope, and so that's why we recommend the alcohol as a way to disinfect, whether it be our wipes or whether it be our hand sanitizers. And in general, the top priority is finding things that are sporicides. If you need to get rid of the endospores, then you have to make sure the chemical disinfectants that you are considering are able to be sporicides.